Now the next example is also translation, but this time it's translation in the original function, right? And that is also nothing. So remember that's two different translations. One is translation in the transform variable, the S, and this one is transform as in the original variable, but we start with what we should guess. So basically now you have the transform, original transform f sub s. Now you know that if you multiply by exponential function, that probably will get you the translation in the original variable, because the inverse is also true. You translate the transform variable, then you get the exponential function multiplied by the original function. So that you can guess that you can work that out to see if that's the case. So basically, you have e to the minus bs multiplied by the transform minus sb fb dt. Right. And you multiply this together minus s, that is d plus b, right? That's the integral ft dt. Now what you can do is we define your variable. We change the variable as t prime, call this t prime, and t is t prime minus b, and dt is just dt prime. But then you need to be a little careful in the limit, because now t prime start with actually t prime is t plus b. T start from 0, so t prime is actually start with b, right? It's b. And then now you assume that that's the extra assumption. Ft is actually a step function, so you start with exactly t with 0. Ft is whatever function, it doesn't have to start with 0. Then you assume it's 0 at the negative t. This is t, and this is 0. And ft is originally like that. So, right. And now so basically now the original function is, you basically change that to ft instead of instead of the original function. This is the same as multiplied by a step function, say the t, right? And again, this is the same as you have a fade. Do the same thing, t prime minus b, t prime. Right. If that one is this is so assuming b is positive, so you have a b here. So this now the figure is getting a little confusing. Yes, say that again. This is just a capital theta. I like to write. I mean, some people like to write it like that, but this doesn't look like a theta. And so I usually just write like capital theta. It's just a capital letter. capital grid letter. Okay. And now what you want to figure out is you start with B, but you multiply by the original function is like that. The only complication is that you have instead of all the Laplace transform defined as start with B, right? So basically now this function means you're still integrating that the same function, just redefine your integration variable that start with B, right? The t is okay. The t prime is t plus b, right? So you draw a t prime axis, right? T prime equals 0 at t equals to minus b, right? T prime equals t plus b, right? T prime equals 0 is at minus b. So this is this actually it corresponds to this minus b, right? And then this is and all these things that so you start with integrating from here, but this point is what we call as t is 0, which is t prime equal b. T prime equal b. So this is this point. So this function, after you change the variable, you actually shift the whole function to the right. This is your function, right? It means this function, which is multiplied by the step function, is like that, right? And then because it's 0 from 0 to b anyway, the function, so you can write your integration variable start with 0 anyway, because 0 to b involving the integram is 0. So minus s t prime f t prime minus b. With this theta function, with the step function, t prime, and then you just call it the Laplace transform of f t minus b. And suppose that you need to have the step function also, but if you not include that like your textbook, it's just implicitly assuming that the original function is like that without actually multiply the step function explicitly. And you write it like that. So that's a little complication with the translation in T rather than S. That is unlike the Fourier transform. In Fourier transform, what I told you go both ways. You can if you multiply by a frequency, shift it in the phase in the frequency of the transform, you just get a translation in the real variable, and without all this complication, because Fourier transform minus infinity, yeah. Inside the truth. This one? It doesn't matter. It is yes. T prime is the integration variable. This is just to say that if you do the Fourier transform of this function, you put in the Laplace transform formula, you get this one. And assuming that you have this truncation of the function for negative t. Right. Okay, so T prime is just what we define it. So that's just integration variable. Yeah. Yeah. Yeah, the only thing changed from this is extending the integration limit from B to 0 all the way to 0. So basically, this line is from B to infinity, just following the original one is from 0 to infinity. If we define your variable, d pi, so integrate from p to infinity, but now you realize that for t pi less than b, it's actually 0, or that's by your assumption, then you can extend it all the way to 0, right? So that's just, yeah, there's no angle. Theta is just, I usually use theta as a step function. Theta of t is 1 for t greater than 0, 0 for t less than 0, and usually the exactly 0 argument is not defined. You can define it as a 1/2 if you like. Okay, yeah. Well, there's example, the wave equation which we have seen, and then using the Laplace transform get this exactly the one that we did in the Fourier transform example. Is either t x minus vt or v x plus vt. So that kind of trivial. So that example is really simple. I don't want to spend the time to do it. Right? It's just directly applying this kind of formula. Okay. So we'll go to the next property. The next property is derivative of a transform. Right. So you have so originally you have this just the definition. T dt, right? And then the derivative of a transform means with respect to the transform variable, so you df ds, right? And now, quite obviously, you just pull out the minus t, and take the derivative with respect to s, right? That's the same thing, same exponential function, multiply a minus t factor, f t. Okay, and now by definition, now this is just the Laplace transform of minus t f t. Right, not too bad. So that's another way to extend your known Laplace transform. If you know the Laplace transform of capital S, then you can keep doing derivative and get another Laplace transform. It's basically multiplied by t, and then this is just take a derivative. So whatever. So if you know a transform of a certain function f, but not the more complicated one, like a certain power of t of multiplying by capital F, then you know the transform of that function by just taking derivative, right? And this is just one derivative, and obviously you will take n derivative. By the same consideration, it's just minus t to the n times, right? Because each time you take derivative, you just multiply by minus t factor up to this n. And you take n derivative, and you just multiply minus t to the n power. Right? Is it obvious? This one, yeah. Okay, so that allows you to extend your known transform formula. Okay. What else? The example of these are really trivial. Just, I mean, the text will list a bunch of them, but yes, quite simple. So you can just look at one of them, say, if you originally we talk about this, the transform cosine. You know the transform cosine, right? That we just talked about that in the damn oscillator example. So you know that this is like this one, except it don't have a minus sign. So you can multiply a minus sign, multiply by or minus sign on the other side. So this is minus BDS of the transform of cosine AT. Right, just comparing this with that. The multiplier T involves a minus BDS. And that is should be straightforward because we know that this is sk squared, right? So you just do derivatives, and first one you take the derivative of the denominator, give you s squared plus k squared square and 2s, right? And then the next one is this 1 over s squared plus k squared. And then you can combine the denominator, 2s minus s. Wait, what? Did I do anything wrong? This one? 2s squared, yeah, right, thank you. The original was s, yeah. 2s squared minus s squared minus k squared is s squared minus k squared, right? Yeah, so that's just a very trivial example, and you can obviously you can keep doing that. And the other example involves a Bessel equation, and unfortunately we haven't talked about Bessel function. I think Bessel function is chapter 16 or something like that. No, chapter 14, chapter 14, but that would be covered in the next semester. And they involve some formula or property of Bessel function, which is also straightforward. But this is like we deriving those property using Laplace transform using this formula. But because we haven't learned, so I hope we won't struggle in and not ask you to just read ahead of the Bessel function. But if you like, I have the old video on my YouTube channel talk about this kind of thing. And it's also long. It's to get to the final equation, the Laplace transform of J sub n. That one involves quite a lot of derivation. So I will skip this example. Okay, so maybe we can revisit that when we talk about the Bessel function. But for now, we will not use that. Okay, and so anyway, this is enough. This a straightforward application that useful formula for you to calculate transform of a new transform, and then the form O transform by taking derivative. And another way to do it is integration. The next property is integrating the transform, except integration you need to define it a little bit carefully because it's a function s. So when you do integration, you integrate with the limit as s. One of the limits is s infinity and f. That you can, well, I think your textbook using x, it doesn't matter. I would say I don't use s prime, but it doesn't matter. So you integrate the transform of s to infinity. And just so what you do is just substitute this into here, s infinity. Now integrate this, put into here. You need to change your variable because that's the x. So this change to x. It's xt, t, dt, and dx. But now you do the x integration first because other are more complicated. So, when you take the derivative, integration of this one is exponential function minus xt divided by minus t limit 0 to infinity, s to infinity. This is s to infinity, right? And the rest is this function t and t integration. Okay. Now at infinity, that exponential function will kill you, right? So that the whole thing will be 0 at the lower limit. So x equals to s. So this is, and this is lower limit, so that's a negative sign. So e to the minus st divided by this t, right? And then t, right? And so that is just the Laplace transform of 1 over t. Right? So this is similar to the, say, we might take a derivative is multiplied by minus t, right? Take the integration divided by t. Now without the minus sign, and that property defined because of the definition, your s is in the lower limit. But it doesn't matter if it's not, it's s is not in the lower limit, it's in the upper limit, then you change to the negative sign, right? Right, and that is another formula. So that's again another way to extend your table of Laplace transform. And